The railway track circuit is the most widely used train detection system in the world. It is an electrical loop running through the rails that helps identify whether the track is clear or occupied by a train. You can imagine the loop like this. The two steel rails act as long parallel electrical wires, constantly carrying a low voltage current from a battery at one end to a receiver at the other. While track circuits are the standard, there is another major alternative. Modern sensors and axle counters offer extremely high precision, but they can be incredibly expensive. That is why for most railways, the traditional track circuit remains the most reliable and cost-effective choice. The DC track circuit is a simple electrical loop, invented by William Robinson in 1872. In this track system, the track is divided into specific sections. To prevent electrical leakage into the next section, insulated rail joints (IRJ) are used. This ensures that each track section stays electrically separate. For maximum durability, many networks now use glued joints, a special type of insulated joint. This insulation is provided by high-strength side channels, bushes, and end posts, all crafted from fiberglass cloth roving. Standard rail joints with fish plates are actually poor conductors. Over time, rust and dirt block the current. To fix this, the joints are bridged by two mild steel wires called bond wires. These ensure a solid, reliable electrical path from one rail to the next. In each section, there is a start and an end point. The start point provides the power source, while the end point is integrated with a relay system. The power source, typically a 4-volt battery, is housed with a regulating resistance inside a protective steel cabinet called a location box or feed box. The current travels from here to the rails via underground cables and a junction box. At the opposite end of the section, the circuit is completed by a device called a relay, which acts as an electromagnetic switch. This specific relay is designed for use in railway DC track circuits within 50 Hz electrified traction areas. The battery end supplies power to the track, where the positive terminal connects to the positive rail and the negative terminal connects to the negative rail. Additionally, an OHE bond, a metal component, is connected to the negative track to maintain electrical balance. Let's see how it works. When no train is present in the section, the electrical circuit is complete. Current flows from the battery at the feed end, travels down one rail, passes through the track relay at the far end, and returns via the opposite rail. This constant flow of electricity keeps the relay energized, holding the contacts in the up position. In this state, the signaling system displays a green aspect, indicating the track is clear. The moment a train enters the section, the situation changes. The heavy steel wheels and axles of the train act as a massive conductor. Because steel has much lower resistance than the relay coil, the current takes the shortcut through the train's axle. This is known as shunting. Since the electricity is now flowing through the axle instead of the relay loses its magnetic pull. Gravity pulls the relay contacts down. This Dropping of the relay immediately breaks the clear circuit and triggers the occupied circuit. The signal behind the train instantly flips to red. Once the train clears the entire section, the electrical circuit is restored, allowing current to flow back through the relay. The relay energizes and the signal automatically flips back to green. That's the basic working principle of the track circuit. Did you find this interesting? Let me know in the comments. Also, if you'd like to learn more about the relay system, let me know below. Please hit the like button if you enjoyed this. Thank you.